Linear regression. We're going to formulate this twice. The first using just algebra, and you'll notice this is ugly, but it leads to an answer that works just fine. The other, we're using a matrix approach, and it's much cleaner and I think much easier to understand. Given that we've derived linear regression and can use it, I want to visualize the least squares, which is how linear regression is happening. And I think it'll give you a little bit more insight as to what is actually happening. Then we'll talk about how to actually implement linear regression. So what is the goal of linear regression? Well, linear. We are fitting a bunch of measured samples to a straight line. And these measured samples probably have noise. They're not going to fit a line exactly. Yet, if we sort of squint our eyes and blur it, our eyes and our mind can somehow see the trend. And we would like mathematically to somehow also fit that to a trend. So we're going from a bunch of measured positions of points to the fit of a line. And those measurements have noise. That's an important element of this. This is the algebraic approach. This is going to be ugly, but it will give us a way to get a best fit. And then the matrix approach later will be much more clean. So we start off with a set of m measured points. So for a straight line, this is a set of m pairs of x and y values. Those are our measured points. We also have an equation for a line. And the equation for the line has two parameters in it. It has the a0 and the a1. Well, what we can do is write this equation for the line, but plug in our x and y values for each of our measured points. Now remember, our measurements have noise. So these equations aren't exactly satisfied. And so the way we compensate for that, and what lets us write equal signs here, we add error terms, and we call these the residual terms. And really the goal of this is for us to choose a0 and a1 such that the values of these residual terms are minimized. So we need some kind of measurement for minimized, how good our fit is. And we need a single number. And we have a set of these residual terms. We might have 100 of them. Somehow we have to reduce this down to a single number of how small all of them are in congregate. So what if we just added them together? Would that work? Well, no, that wouldn't really work because we're going to have some of them that are negative, some of them that are positive, and they will tend to cancel, and our overall error metric will be smaller than it should be. All right, what if we added the absolute values of those errors? This is better, but it turns out this does not lead to a unique best fit. What if we summed the absolute value squared of all those error terms? Well, it turns out this works, and this is what we will do. So we picked a good criterion for best fit. Let's actually derive an equation for it. So if we look at the equation for the mth sample, so it's one of our intermediate points here, let's proceed with this. The first thing we'll do is solve it for that residual term. And now we're going to take a look at what's on the right-hand side of that equation. If we look at what's in parentheses, it turns out that is our fit value of y at x equals m. However, because there's noise in our measurement, the actual measured value of y makes it so that these two aren't the same, and that's why we got the residual term to begin with. So over here is our measured value of y, and in parentheses is our fit value of y. So our error criterion is we're adding up all of these residual terms squared. Well, the residual term is the measured minus the fit. And then, of course, we'll square that and add them all up. So we essentially have our measured value of y minus, we're taking this, we're subtracting what's in parentheses here. And that's why there's a minus sign on both of them. We're subtracting the fit value of y. We have our error criterion, and we would like to minimize it. What's a common way we know to minimize a function? Well, there's the first derivative rule. What if we differentiated our error criterion with respect to a0, a1, set those equal to 0, and use those equations to figure out what values of A0 and A1 make that happen. When we solve for our A0, A1 by this technique, this is called solving the problem in the sense of least squares, because we've minimized the squares of the residuals. Let's go ahead and differentiate our error criterion with respect to each of the unknowns. First, we'll differentiate with respect to A0. So we write our partial derivative operating on this summation. This summation is our E, our error criterion. We can bring the partial derivative to inside the summation and now apply it to the expression in parentheses squared. And we use the chain rule to do this. So the squared comes to the outside, the expression in the parenthesis remains unchanged, and we have a -1 here that comes to the outside. And we can do a little bit more algebra to simplify it. And here's our final expression for the error criterion differentiated with respect to A0. We do the same thing with respect to A1. We'll bring the partial derivative inside. We use the chain rule, so the squared comes to the outside. The derivative here is a minus xm because we're differentiating with respect to A1, so we get our minus xm here. And we can bring the minus and the 2 to the outside. And here's our final expression for the derivative with respect to A1. Step 2 is to set our derivatives to 0. We derived expressions for the derivatives on the previous slide. Here, we set them equal to 0. So this is what we derived on the previous slide. And now we can write this as 3 summations. We can't do anything with the y sub m or the x sub m, but in this summation, we have m occurrences of A0. So we can get rid of the summation and write that as m times A0. We had our other partial derivative. Here we separate it into 3 summations, and we really can't do anything further with that. So at this point, we have 2 expressions. What we'll do is we'll rearrange them so that we have the y terms on the right and then everything else on the left. And we can look at these now as 2 simultaneous equations that we solve for A0 and A1. And by the way, these are called the normal equations, these equations at the bottom. So we need to solve them simultaneously for A0 and A1. After a bit of algebra, here's where we end up. We have a nice expression for A0 and a nice expression for A1. Well, you know what? That's actually not so nice. In fact, I would say yikes. There has to be an easier way. And in fact, there is. That's the matrix approach. So in this first equation, we have the average of y and the average of x. So here's our equations for calculating the averages. But that's how we can calculate A0 and A1 to fit a set of m points to a line. Linear regression, the matrix approach. This is the clean approach. This is the way most people implement it. We're going to state our problem a little bit different here. Since we have a cleaner approach, we're going to generalize this so we have any number of independent variables. Before we talked about just x and y. Now we can have x, y, z, and even more. So what was x, y, and z, we're now just writing as all z's in this equation. And of course, multiplying each one of those is an unknown coefficient that we have to find. That is our curve fit. So f is our measured value. The z's are the data, the position from which we're evaluating f, and the a's are the unknown coefficients. So what we'll do is we will write that equation once for each of our m measurements. And notice we've just automatically incorporated these residual terms here. We didn't do that as a separate step. This large set of equations we can put into a matrix form. And on the left, we simply just had all of our measured values of f. We'll store those in a column vector. These unknown coefficients, A0, A1, A2, A3, all the way up to AN, we store in a column vector. Multiplying these are all of our measured values of z, which are independent variables, x, y, z, or anything else we might have. And then our residual terms are in another column vector. Now notice the number of terms in this residual column vector is not the same number of terms. We probably have many, many, many more equations then we have unknown terms that we're trying to fit to. So these are of different lengths. So there's the same number of rows or same number of elements in this residual column vector as there are in the F column vector. But that's not the case for the unknown coefficient column vector. So this is rather busy, and rather than keep writing it this way, there's two ways that you'll see this written more compactly. I tend to like to use lowercase letters for column vectors, although there's times I have to deviate from that. Uppercase letters for square or rectangular matrices. So here's our F, here's all of our Z's in that big square matrix, here's our column vector of line fit coefficients, and then this column vector of residuals. And so we can also write it this way, and I like to use bold letters that they're kind of these fat things that contain a lot of numbers. So either way, it's more compact notation. Now we're going to derive our solution where we're finding the solution in the sense of least squares. So starting with the matrix equation we had on the previous slide, let's solve for this column vector of residual terms. So here we are, and this is what we want to minimize. Well, before we had arrived at this best fit error criterion E as the sum of the square of these residuals. Well, we're storing these residuals in a one-dimensional array. So if we write this first as a row vector and then a column vector, and if we multiply these together, this is actually what we get, the sum of the squares. And so a neat little compact way to write that is E transpose times E. Okay, so our best fit criterion is E transpose E. We previously have an expression for the residual terms in terms of F, Z, and A. So we can just write that in there. And we'll proceed with that. We're going to want to manipulate the equation we derived on the previous slide because we're going to have to take its derivative with respect to this column vector A. And so we want to manipulate this in a way that makes that easier. So we have our original equation, and we will distribute the transpose into the left-hand parenthesis. Then we're going to multiply everything out. And then we'll stare at this for a while. And what we're going to realize, this is a single number constant. So every term in this expression is just a single number constant. And if we look at these two things, we'll realize that they're actually equal because they contain the same terms in there and they reduce to a single constant. So we'll just subtract 2 times one of them. We combined the terms. That's one less term to take a derivative of. To do our first derivative rule, we need to differentiate E with respect to A. And this may seem kind of strange. This E is a single scalar number, and we're differentiating that with respect to a column vector of a bunch of different numbers. Well, what's really happening, and it's all happening at the same time, is we're differentiating E with respect to each one of the parameters in here individually. But we can do it all at the same time by sticking with our matrix notation. So we start off with our expression for E. We now take the derivative of E with respect to A. So we're just writing our partial derivative outside of our original expression. The next step is we're going to apply our partial derivative to each of these terms individually. And we end up here. Now this first term, these F's, these are just column vectors of measured values. So they don't depend on A at all. So if we differentiate those with respect to A, this goes to 0 and that term disappears. On the second term, the 2 comes to the outside of the derivative and nothing changes over here. There's no constants to bring to the outside. Now we want to do those derivatives. And so when we differentiate this first term, this A is sort of just a constant. So we're really just left with 2 times ZT times F. Now over here, we have 2 occurrences of A. Think of that as like an A squared. So when we differentiate it, the 2, the squared, comes to the outside, and we're just left with the Z transpose times Z times A. We will finish our first derivative rule by setting it equal to 0, which is what we're doing here. Well, we see this term that has a negative sign. It would be convenient to bring that over to the right-hand side and get rid of the negative. At this point, we can divide both sides by 2. And now this is very easy to solve for A. We simply take this expression here, Z transpose Z, take the inverse of that, and pre-multiply both sides by the inverse. So the inverse times itself, we just get the identity matrix. So it really just disappears over here, and we get the Z transpose Z inverse on the right-hand side. Now I want to make an observation because in practice, this is how we implement it. This equation here, notice ZA equals F. That's actually our original equation that we had to solve. And what we've done is we've pre-multiplied both sides by the transpose of Z. And so that actually implies how we actually solve problems by least squares. So we had this expression, and here's just sort of a warning. We don't want to simplify this further. This actually is how we solve it numerically. And so what happens if we were to simplify this? Well, first thing we might do is distribute the inverse into what's inside the parentheses. Now we have a Z transpose inverse times a Z transpose. That will give us the identity matrix, and we're just left with Z inverse times F. So all of the least squares stuff we've just done has vanished. So we actually have to solve it this way. Visualizing least squares. I will admit, when I am looking at linear algebra equations, I am trying to visualize it this way, where I'm looking at the sizes of things. So our original matrix equation has lots of rows in it. As we had lots and lots of measured samples, probably not so many things we're fitting to. So the height of this is equal to the width of this. So the same number of columns here as the rows here. So our original matrix equation looks like this, that we want to solve by least squares. Well, what did we do then? Well, we took this matrix and pre-multiplied both sides by its transpose. So its transpose kind of lies it on its side like this. So what was a tall rectangular matrix is now a long horizontal rectangular matrix. So if we take this matrix and we so this long side-to-side rectangular matrix and pre-multiply a tall rectangular matrix, we get a square matrix. And then on the right-hand side, we get a small column vector. And this is now a rather small, compact, simple AX equals B linear algebra problem that we can solve by conventional means. But this last few sequence of slides is very much how I visualize linear algebra equations, and it helps me understand really what's going on. Implementing linear regression. Solving something by least squares is 3 simple steps. Remember what we're doing. We have a whole bunch of measurements that we're trying to fit to a linear equation. So we have a whole column vector of measurements F and a whole column vector of really the positions of each of these measurements F. So what we'll do is we will take this matrix Z and calculate its transpose, and we will calculate these unknown coefficients for our curve fit, not a curve fit, line fit this way. A equals Z transpose times Z, that inverse, times Z transpose times F. Remember not to simplify this. This is actually how we have to calculate it, or we erase all of the linear regression stuff, the least square stuff that we did. Once we have that column vector A, then we can go in and read off the different coefficients for our line fit. So let's say we just have a problem AX equals B, and there happens to be a whole lot more rows than columns in this, so we have many more equations than we have unknowns. That's not really solvable exactly, and so we would want to solve this as a best fit. And now we know how to solve this in the sense of least squares. And so the way this works is we have this original equation AX equals B. We will calculate a new A and a new B. And we calculate those by pre-multiplying by the transverse of the original A. Now we have a new AX equals B equation that's actually much smaller than the original one. And we have an A prime and a B prime. But just think of this as a new AX equals B. And if we solve this, we get our answer X, as if we had solved this one. and it's a best fit. Let's do an example. So let's say we have these points and they look pretty good, but there is some noise in there. We would like to fit those 4 points to this line and calculate what M and B are, and then probably plot our line through those measured values. So we know we have to write that equation for the line 4 different times for each of our 4 measured samples. We can put these into matrix form. So we have our measured values of Y, we have our 2 unknowns, M and B, and here's our values of X1, and then there's just ones multiplying these B's, so we just have a column of ones here. So our F, if you will, from what we've been talking about, is our column vector of Y values, and this matrix with the X's in it is our Z matrix. We solve this in the sense of least squares, so we will take this Z matrix and we will pre-multiply both sides of the equation by the transpose of that. The next thing we'll do is we will multiply these 2 matrices together to get a square matrix. We will multiply these 2, this matrix, by this column vector to get a reduced column vector. And now this is solvable. We can multiply both sides by the inverse of this matrix, or we can think of it algebraically, taking this matrix, bringing it over to the other hand side, and solving this for M and B. So we extract our values of M and B from that final column vector. And once we have that, now we can plot our line. And we can plot our line through those points, and we can now even visually get an idea of how much noise there was. There was very little noise to begin with, but this looks like the biggest outlier right here. So we did a curve fit using linear regression. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.